Hello, in this video we're going to revisit the idea of linear independence. So let's begin with a definition. Consider the set of vectors v1, v2, v3, all the way up through v sub n, and scalars c sub I, such that c1 times vector v1 plus c2 times v2 plus c3 times v3 plus dot 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 all the way up through c sub m v sub m equals 0. If there exists scalar c sub I, not all 0, that satisfy the equation, then we say that the set of vectors is linearly dependent. If the only scalars c sub I that satisfy this equation are c1, c2, and so forth, all 0, then we say that the set of vectors is linearly independent. I'd like to draw a picture so that we can get a more intuitive understanding of what those terms refer to. Okay, so let's begin in 2D. So let's suppose we have two vectors. Let's suppose we have two vectors, v1 and v2. And again, we're in 2D. So we're just plotting on the Cartesian plane. And so in my first example here, I'm going to draw v1 and v2 for this particular choice. So let's say v1 is the vector 1, 1, and let's say a v2, we'll put in a different color, v2 is a vector 2, 2. Now we can tell right away that these two vectors are going to be collinear. So there's vector 1, 1, we'll label that v1, and vector v2 is collinear with v1, it just has a longer or greater magnitude. In this situation here, we call these vectors collinear, so these vectors are collinear, and we say that they're dependent. So why are they dependent? Well, we say v1 and v2 are dependent. Notice that v2 times v1 is simply equal to v2. In other words, v2 depends on v1. Whatever v1 does, 2 times it is going to determine what v2 does. So they are dependent. And having this equation, this idea that one vector is a scalar multiple of the other, they're collinear, really does lead us back to the definition of linear dependence. So if we were to subtract v2, we would get 2v1 minus v2 equals 0. And notice there are the c sub i's. We've got c1 and c2, so there's c1 is 2 and c2 is a negative 1. The c sub i's are non-zero. We've got non-zero c sub i's that satisfy this equation, and this brings us back to the definition of linear dependence. Okay, so linear dependence if there exists scalars c sub I not all 0, and we certainly did that for this collinear case. Okay, so let's contrast that with a different example where we are still in 2D, we're graphing in the XY Cartesian plane, but now let's take a different choice for v1 and v2. So we'll let v1 be 1, 1, and let's let vector v2 be over 1 up 2. Okay, so here's our first vector, v1, and here's vector v2. And you might be wondering, are these vectors linearly dependent? Are they linearly independent? Well, it's not quite obvious from the picture, at least the first time you see this, whether or not they depend on each other. I mean, maybe there is some way, maybe, of writing scalar c sub I times v1 plus c2 times v2. Maybe there's some way of getting these this linear combination to be 0. We don't know. We have to investigate. So let's work through this and see what we get. I'm just going to extend our little divider down there. So if we work through this, c1 times vector v1, which is 1, 1. And we've got some scalar c2 multiplying times vector v2. And we want to know, how's that going to be equal to the 0 vector? Well, scalar multiplication and addition on this left-hand side will give us a c1, so right there, and then we get a plus c2. And then in our second component, we get a c1, and second component here, we get 2c2. This gives us two equations. We get c1 plus c2 equals 0, and c1 plus 2c2 equals 0. We put this into an augmented matrix, and when we perform our elementary row operations, we get down to 1, 0, 0, 1, and we do determine that the only possibilities are the c sub I is all 0. And so this is the case of linear independence. Linearly independent. And so in 2D, it's pretty clear. If we have vectors that are collinear, they are dependent. If we have vectors that are not collinear, if they lie off of, they're not on the same line, that is what we mean by linearly independent. All right, let's look at what happens in R3. So let's take a look at a picture in 3D. So let's consider some vectors that live in R3 and think about what kinds of linearly dependent pictures we could draw. Well, certainly we've already discovered that if we have a vector v1 and a v2 that are collinear, and maybe even a v3 if you want to get fancy, if they're collinear, we're still looking at a dependent situation. So collinear in 3D means that the vectors are linearly dependent, and you could verify that as well. Another situation that can arise in 3D, and it's a little bit more interesting, is if you have two or perhaps three vectors. Let's take a look at three vectors that are coplanar. So these vectors are going to be coplanar. And for ease of drawing, and it doesn't always have to be this case, but just for ease of drawing, I'm going to draw them all in the YZ plane. And it doesn't always have to be that way, but it's going to make our picture a lot more understandable. So let's let V1 be the vector 0, 1, 2. Let's let V2 be the vector 0, negative 1, 3. And let's consider one additional vector here, V3. And V3 will be the vector 0, 1, negative 1. So let's plot those vectors. So our first vector is out 0 in the x, 1 in the y, 2 in the z. So it looks something like that. Vector v2 is out 0 in the x, it's negative 1 in the y, and up 3. So there's v2. And v3 is out 0 in the x, 1 in the y, and negative 1 in the z. Oops. These vectors are all in that plane. They are all in the YZ plane. So those vectors are all coplanar. So the question is, are they linearly dependent or independent? And we could certainly work through the calculations here. So let's check if V1, V2, and V3 are linearly independent. And again, that check works out to looking for scalars C1 times V1 plus a C2 times V2 plus a C3 times vector V3, and setting that all equal to 0. And if you work through these calculations, again, we're going to set those column vectors up in our matrix. So our matrix would look something like 0, 1, 2, a 0, negative 1, 3, and a 0, 1, negative 1. When we perform our elementary row operations, what we get is 1, 0, 2 fifths, a 0, 1, negative 3 fifths, and 0, 0, 0. And what that tells us in terms of the C sub i's, if we label the C1, C2, and C3, we find out that C1 equals negative 2 fifths times C3, and C2 equals negative 3 fifths times C3, and C3 is a free variable. So let's set that equal to t. And so we have infinitely many solutions. But you know, the question we're really asking is, are there non-zero C sub i's that satisfy this equation? And the answer is yes. Letting t equal 1, for example, we get C1 equals negative 2 fifths, C2 equals negative 3 fifths, and C3 equals 1. So certainly there are non-zero C sub i's that work, implying that indeed this is a linearly dependent set of vectors. And one way of thinking about this is that, you know, linearly dependent vectors, they somehow don't make use of all dimensions that are available. Right here with the collinear case, they only made use of one dimension out of the 3 that are available. And here for these vectors that are coplanar, these vectors only made use of 2 dimensions out of the 3 that are available. The last example we might think of in R3, let's look at the unit vectors pointing in the x direction, the y, and the z. And we've encountered these vectors perhaps in other courses or calculus classes, things like that. But here's our vector v1, here's v2, and here's v3. And so we can certainly see that these vectors are not collinear, they're not coplanar, they do make use of all dimensions. And we could go through the steps and verify that this is a linearly independent set.